Hi everyone, welcome to the COMP1511 revision session. I'm Lucas and joining me today is Adrian, Dorothy, Emily, and Sophia. And okay, before we start, can we just please fill out this attendance form? So in today's session, we'll be covering 5 key topics in 1511. We have arrays, strings, memories, pointers, and linked lists. And once you get a grapple of all these top concepts, you should have a really solid understanding of 1511. Okay. So first of all, arrays. If you want to store, for example, a really long, if you want to store a set of data that are of the same type but really long, for example, in day 1, day 2, day 3. For example, you're a potato farmer and you want to store how many potatoes you store in each day. This becomes too long and arduous, and we need a data structure to store this properly. And to do that, we have an array. Next slide, please. So an array is a data structure that collects variables of the same data type. And they could be stored in various ranges of data types like ints, characters, doubles, and they always index starting from 0. Okay, so there are 2 diagrams here. One, we have int x, and we set the array as the size of x. And the other one, we define size equals to 10. And does anyone know why we define the size of the variable before we cite it? So if you want to do int x equals to 10 and int array x, the reason why that's bad is because does the size of the array ever change? Could you have a longer array after setting the size? No, right? Yeah, that's why we have a slash define, because we already know what the size of the array is going to be. So then we don't need a variable to set it. We can just slash define it. So this is just good code practices to do. Okay, so now we have the size. We want to store data, right? So these are the three data types that we can store into an array. So first one we have int array 1 4. Does anyone know what the 4 inside means? Is the what, sorry?
Index.
Index? Close. So if we look at this, int array 1 4, that's initializing the array, declaring the array, sorry. That's declaring array of size 4. Yeah. So that means that there are going to be 4 sets of data in the array. And since in the int, we're storing 8, 2, 1, 4, which are all integers. Okay, so now character array 2, 3. So 3 is obviously the size of the array again, and we're storing characters, 3 characters in the array. And we put these cursive brackets just because of the syntax of C. That's just how it works. And lastly, doubles. Does anyone know what doubles are? What else do we call doubles? It starts with the F. Floats, yeah, nice. So these are just floating point numbers that we're storing in each index of the array of size 3. And in the actual array, in the memory that these data are stored in, they are in 1.2300000000. There are many zeros behind it. But then just for the sake of demonstration, I deleted all the zeros abbreviated for the sake of a clearer understanding. Okay, so anyways, next slide. Okay, so we're printing array of index 2 from this index from 1 to 3, and we have the elements 8, 2, 1, 4. What does this print? 1? Yeah, nice. That's exactly right. It prints 1 because we're starting from the index 1 all the way to 2, and %b is just the data type of int. So yeah, next slide. Yeah, so 1, nice. Okay, to access all the elements in an array, we start from an int I equals to 0, because arrays always start from an index 0, and we print each value of the array, and then we increment I. Does anyone know why I has to be less or 4, not equal to 4? What happens if I is equal to 4? Yeah, we'll count 5 times, right? This one's 0, 1, 2, 3, 4. And array 4 will be out of range for the example I had previously, because the 4th element is array index 3. So then you get an error out of range index or something like that. So this is why we only go up until 3. And when it reaches 4, the while loop ends. And you can do this with a for loop too, but I just did a while loop for this case, yeah. Okay, one thing about arrays is that you can't assign array to another array variable. So for example, if you have an array A of size 7 with all these ints here, we can't assign array B of size 7 equal to A. And the reason that is because arrays, we'll cover this later, but arrays are kind of just data values in the stack that we'll cover later that they just increment from one in the memory. And we can't just copy an entire array into another. We have to use a different function that we'll cover later. So this is just something that you can't do. Okay. Now Emily will be covering 2D arrays.
Okay, so 2D arrays. So there's 4 main parts of 2D array. So first is the data type, so it can be like int like this one, or char, or float, and etc. And then the name of array, so you can name your array whatever. So in that case, in this case, it's array. And then the size. So this is like the most important part of a 2D array, is that the first like square brackets are the rows, and the second are the columns. And then lastly, you would want data to populate the array. So in this case, we're declaring it in array with 2 rows and 3 columns. So we need to put like match that data. So yeah, to match that data, so it works.
Ask if anyone has any questions. Maybe.
Yeah, does anyone have any questions so far? Okay, let's keep going. Okay, so this is just sort of like a visualization. In this case, we have 3 rows and 3 columns. But as Lucas said, since our index always starts at 0, then row 1, column 1 would be 0, 0 instead of 1, 1. So yeah, that's it. Next. Okay, so okay, this is a short exercise. When I print the character, what will be the output? Does anyone know? Anyone? Any ideas? The output should be B.
Yeah.
Because it's saying the index of row is 0 and then the index of column is 1. Since we're starting like row 1 would be index 1, so we looking at the first row and then the second column. So yeah, that's why it's B. And that's like a visualization of it. Next. Okay, so probably the most important part of the 2D array is knowing how to traverse it. So when we traverse it to the array, we'll use 2 for loops or like 2 while loops, but for loops are like probably a bit easier. So we go through each column within the first row, and then we check each column, and then we go to the next row, and we check each column within that. So that's why the column for loops on the inside. So yeah, this is just like a simple for loop that should print out all the elements of an array. Yeah, and that's just a visualization. So go to row 1 and then go through each column. Any questions? Okay, let's go to the next one. Okay, so now we're gonna do like a coding exercise. So count consecutive rows. So given a 2D array, return the number of rows in which the values are consecutive. So for example, 1, 2, 3, 4, that's consecutive. So then we'll add 1 to the count because that's a consecutive row. But then if it's 2, 4, 5, 6, that's not consecutive. So yeah. So I'll show you how to do that. Okay. Count consecutive. Hello? Wait, that doesn't work. Okay. So first, when we start, we'd want to create a counter, right? And the reason why we make a counter is because we're counting the consecutive rows. So we just initialize it int, and I'm going to call it count, and we initialize that to 0. So if I'm wanting to count each consecutive row, I'm wanting to like traverse through each each number inside the array, right? So how would I do that? How would I traverse through each element? Yep. So like as I said before, you just use 2 like for loops. So first, I'll use the row for loop. And then I'll make a second for loop, which is the column one. So it should be like that. And then I'm just incrementing that. Okay. So firstly, does anyone have an idea of how I would start this code? Okay, all good. So I'll start this by creating like a flag, right? So what that flag is I'm checking if one of these rows is consecutive or not. And I'm going to initialize that flag to 1. So basically when I initialize to 1, it just means, oh, it's true, right? Because 1 is true and 0 is false. So as I'm checking through each column inside the row, I'm going to put like an if condition. And this condition is, so that's how I access the current element, right? And then I'm going to put this second condition. Okay, and this might seem like a little confusing at first, but what it's saying is, well, first of all, I'm starting with j equals 1. And the reason why I'm doing that is if you see in this sort of line, right, j minus 1, if I was to start at 0, right, then my array would access the index minus 1. But since the index always starts at 0, that'll be out of bounds. So that's why we start at 1, and I'm basically checking this condition. If the current element in the array is not bigger than by 1 of the element before that, then I'll break out of the loop, basically. So yeah, so I'm gonna, if that condition is not true, I'm gonna set I'm gonna set is consecutive equals to 0. And then at the end of the row, so after I'm finished checking the columns, what I'm gonna do is put another if statement. And if it is consecutive, wait, why is it not working? Is consecutive equals to 1. So if it is consecutive, oh, so if the is consecutive part is true, then I'm going to increment the count by 1. So yeah, that should be it for the code. And now I'm going to run it. Control. Wait, why is your So I'm going to compile the code now. And hopefully when I run it, I have these 3 like test arrays, right? So as you can see, like in the first one, the consecutive rows would be 2, right? Because 1, 2, 3, 4, that's consecutive. 4, 5, 6, 7 is consecutive. In the second one, all of them are consecutive. And then in the last one, it should be 0. Oh, wait, no, 1, I think. So hopefully when I run it, that works, maybe. Is that right? Oh, count. Okay. Oh, okay, so I made a mistake. Yeah. Yeah. Did anyone catch that mistake? I didn't return count. Yeah, I did that on purpose. So now we're gonna recompile the code. And when we run it, yeah, 2, 4, 1. So yeah, that's it. Yeah, are there any questions about that? Oh yeah, are there any questions? Yep.
Can't you just increment your counter like within the loop?
Oh, like why is this not inside the
Yeah.
column?
Can't you just replace is consecutive equals 0 with count plus plus?
That's a good question.
Wait, so are you saying that you're putting count into this one here?
Yeah, and just get rid of the boolean.
Okay, so what do you think count is in this case?
Count is the counter where if it is
If it is consecutive, you increment it. Yeah, nice. Okay, but if you look here,
Oh, yeah, I get it.
if you increment counter here, this is when array ij not equals to array ij minus 1 plus 1. Okay, so if we have an array, this will be hard to visualize, but imagine you have an array that's, for example, 2. And then the array before that is, let's say, 0. So then array ij is 2, and the array ij minus 1 is 0. And so 2 is not equal to 0 plus 1, which is equal to 1, right? So since they're not consecutive, we have this consecutive equal to false flag. So then if we increment count here, we're incrementing count when they're not consecutive, so that will return an error.
I mean, but it's only going into like that part if it satisfies the if loop, isn't it?
So I think the reason why is because if I'm like putting the counter inside, then as I'm checking through each column, then I'll increment 1. So I'm not actually finished, like waiting for the entire row to finish, because I need to check if the entire row is consecutive. If I increment it by the count, it's just like these two. So that's why that wouldn't work. But yeah, that's a good question. Any other questions? Okay, thank you. Now we'll be moving on to strings.
Yeah. I'll do that.
Alright, my name is Adrian and I'll be talking about strings. So, a string. A string is an array of characters. Yeah, it's basically just an array, but each element is a character. And it forms a word. So like here, party, and element 0 is P, A, R, T, Y. And the important thing to note is that at the end of a string, in the array, you have the null terminator. Yeah, any questions with that? No, okay. So we have two main methods of printing a string. So method 1 is using a loop, and the other method is using %s when we print. Okay, so this is how you print a string using a loop. It's probably like the inferior method, but yeah, okay, that's pretty tedious. But anyway, basically we just go through, similar to how we loop through an array, and we keep looping through. We set I as like the counter, and then we terminate it when the current character, so word index I, is equal to the null character, into the null terminator. And in each iteration of the loop, we just print the current character. Yeah, any questions with that? No. Okay. And method 2 is using %s. So this is like the superior method. Basically, just use %s in the printf statement, like that. Okay, so yes or no question. Can I print a string? Oh, can I scan a string using this? No? Why?
Memory release or something.
Yeah, it's like a buffer overflow. I'll explain. So, go next. So, fgets is like the safer method. And the reason for that is because scanf just sucks in general when scanning in strings. Because let's say max len. Okay, max len is 100 here. But what happens if the user types in like 200 characters, right? Then, yeah, it's like a memory leak. Well, it's not a memory leak, it's a buffer overflow. So the amount of memory that string is defined as, like, it just gets overloaded, so it causes an error. Whereas this is safe, because in fgets you set the max length. So whatever the user enters, only the max length will go into the buffer. Okay, so now we'll talk about some common string functions. Yeah. So we have string len. This is pretty useful. It's calculating the length of a string. So hello would be return 5. We have string copy.
Wait, it says return 6.
Oh shoot, my bad. There was a space. Okay. String copy, which is you copy a string into another empty variable, or it doesn't have to be empty. So here it would make, okay, what would the value of str be after this? Yeah, exactly. And we have string compare. So it returns 0 if string 1 and string 2 are the same, and 1 otherwise. Yeah, any questions with that? Okay, cool. Now we will move on to memory.
So hi guys, I'm Sophia and I'll be talking about memory. So firstly, memory is the part of the computer where a program stores data and instructions while it runs. So this includes your function call info, your function variables, and data structures, anything like that. And how memory is organized is in contiguous blocks of cells, each with a unique address. So these at the bottom, there's 0x74, 0x78. They all represent memory addresses of these blocks of memory. And within these blocks of memory, you have the values that you give it, basically. Yeah. And there are two ways where data can be stored on memory. We have the stack and the heap. And when we talk about the stack, everything on a stack is basically gone after you finish your function. So your ints, anything you declare, your ints, your chars within a function is called to the stack, or anything related to that function call itself. But once you exit the function, that stack is deleted. On the other hand, heap might be newer. We use malloc to assign memory to heap. And so malloc, the function malloc is used to dynamically allocate memory as needed. So in simpler terms, we just allocate as much memory as we need. We just take as much memory as we need, and we don't sort of take too much that we don't currently need. It reserves a specified amount of heap memory, and most importantly, it returns a pointer, which we'll be going through later, to the first byte in that in the stuff you malloc. Does anyone have any questions so far? And how to use the malloc function? So firstly, we declare what type of data type you want to use. So it could be an integer, could be a character, could be a double. And then we have our pointer, which I call PTR, and we have an asterisk in front of the pointer because it's a pointer. And what that does is it basically points to the first byte of the block of memory that we have malloced. And then we have the malloc function, and then a bit of simple math. We have x as the number of elements you need or you want to assign memory for, and then you have size of int, which is the specific data type. So if we want to reserve memory for, say, 4 integers, we'd have 4 as x, size of int. And really important to note is whenever we malloc something, we always have to free it when we're finished using it. So why we do that is if we keep mallocing and mallocing, we keep taking memory and we're never giving that memory back, right? And eventually that memory in the computer is going to run out. And if we're not freeing, this may cause a memory leak, and that's just really bad for your program. It'll cause all types of bugs and errors, issues. Yeah. Does anyone have any questions on memory? No? We just go through pointers.
Yeah.
Okay, so now let's do pointers. Okay. So what's a pointer? Does anyone know? Okay, we can find out. So a pointer is a variable that stores the memory address of another variable. Yeah. So you guys are probably asking, so why should we use pointers, right? Why do we have to use pointers? Why can't we use ints or whatever? So there's 3 main reasons. The first one would be to access dynamic memory. So as Sophia said, we can use malloc when we use pointers. And this allows memory to be allocated during the runtime, and this is really useful, in comparison to arrays, right? Because arrays, we always have to define it within a specific size. But malloc, we can we don't need to know the size of it in advance. Yep. So the next reason why pointers are so good is because when we can pass large data structures by reference. So what this means is when we're using functions and stuff, we don't have to like edit the exact function of it. We don't have to edit the variable, right? So we can go to the address of that variable and modify it instead of like modifying like a copy of it. So yeah, and this speeds up programs and allows functions to modify original data. So the last reason why pointers are good is because it's essential for using advanced data structures. So we're going to be going over like linked lists later, but we use pointers because they enable flexible, non-contiguous memory layouts. So what this means is like in memory, in array, they're all stored next to each other, right? Whereas in a linked list, memory can be scattered all over the place, even if they're like the linked lists are like pointing next to each other. And pointers connect nodes and make structures like linked lists and like a lot more different structures. Okay, so there's three parts to a pointer. So the first part would be declaring a pointer. Okay, so this is where you'll specify what type the pointer points to. So here I have like a line, so int star num. So what we're doing this step is we're declaring a pointer called num with the int pointer data type, right? And yeah, that's it. Does anyone have any questions? Okay, cool. So the next step is initializing it. So in this step, it's pretty important. We're assigning the address of a variable using ampersand. So yeah, next. Okay. So we have our line from before we're declaring, right? And then I'm declaring another variable called x, and I'm initializing x to equal to 1. And then in this last step is the important one, where we're initializing a pointer, right? So we have num equals ampersand x. And what ampersand x means is the address of x. So as you can see in this diagram, right? When we initialize num to the address of x, we're storing like the address of x in the num. And as you can see, like num is the pointer to x now. So yeah. Yeah. I think I already said that. Next. Okay, so lastly, it's dereferencing a pointer. And we use an asterisk, so the same as declaring one. And what we're doing when we're dereferencing it is we're going to the address that the pointer variable is assigned to. So in that case, like the address of x. And then we're finding what value is at that specific address. Okay, so we have the same code from before. Declaring and initializing, and then add two more. Wait, next. Yeah. So now I'm in this line. I'm dereferencing it. Right? I'm making a new integer called value, and I'm doing asterisk null. So if this code is to run properly, what would it print out? Yeah, that's right. The reason why is because like num right now is pointing to the address is pointing to x, right? So when we're using the star, we're grabbing the value that is stored at num, which is pointing to x, right? So that'll be 1. So next slide. So yeah, that's it.
Okay, now we're gonna look at this with reference to a stack. So on the left hand side, we have int num equals to 6. Okay, so what are we doing here? Are we declaring? So we're declaring num as a data type int, and we're setting the num into 6. So what that looks like on a stack is here. So this is a block of memory in the memory stack of whatever function this is in, and the address of the memory isn't important for 1511, but in this case we call it 0x4, and it goes up in multiples of 4 or whatever. And at 0x4 we're storing the number 6, and this is like the alias of this whole memory block here. Okay. Now we are using the pointer. So we are declaring a pointer int star pointer, and pointer equals to ampersand num. So so what is actually the data type of a pointer? Is it the star itself? Was it the int star? Was it just the int? Yeah, nice. So this is the int star. So what this actually looks like in the code is int star space pointer. That's how when you compile it, that's how the code reads it. So now we are pretty much declaring a pointer of type int, and we're pointing it into ampersand num, which is the address of num. That's why in here, ooh, I think this is a mistake. This should be 0x4, because in 0x8, we are declaring a pointer that's pointing to the number here. So this is not 0x8, it should be 0x4. Okay, so, okay, now, what is the output of this code? So give this a read and let me know what the output of A and B is. Two, one. So which one's two, which one's one? A is two, B is one. Close. Okay, so the correct answer is A is sorry, go back. So the correct answer is A equals to 1 and B is equal to 2. And okay, we can try this out in real code. So let's just okay, so we have int A equals to 1, int B equals 2. Let's call this 2. And we're passing A and B down into this function here. Okay, so let's compile this. So, okay, it's setting A equals to 1 and B is equal to 2. Does anyone have an idea as to why that's the case? Yep.
Is it because after you get to the function, like this naturally returns new values A and B with this one stack, and it gets deleted after that?
Yeah, exactly. So we're passing in A and B into this function called swap. And what essentially happens is, in this function, it actually creates a duplicate variable called the same name A, and it conducts a swap in here, but nothing happens to it because it doesn't get returned, so the whole stack gets destroyed. So I can actually call this int number 1 and int number 2 because they're not actually referring to the same variables as the ones before. So what this subfunction does is just creates a duplicate of A and B and swaps it and destroys it, essentially. Okay, so how do we think we can fix this without returning any functions, without returning any values, by just using a pointer? What can we put into A and B swap that could make the swap actually work by keeping this a void? Does someone have a hint? So should we put the actual value of A, or do you think we should put the address of A? Address, yeah, nice. So instead of swap A, B here, we're going to use this ampersand to pass in the address of A and B, so that we're not creating a duplicate. Okay, so now in here, what should we write in front of before A? Should we write ampersand or should we write something else? Int star, right, nice, because this is passing in an address, and the only thing that can receive an address is a type of int star. So this is the data type, and you're passing the address. Okay, so we're doing this to B as well. Okay, now we should change this to here. Okay, so we have this int temp equals to A. What should we do to change this one? Because right now this is just the int temp. There's a integer A. Yep, nice. So int star temp equals to A. So right now temp has the address of A. And how should we, so does this thing change here? Sorry? So you have int star equals to temp A. So this is a pointer that's receiving.
An address, right? Because, but then remember when we declared, so when we declare a function, for example, let's call this int c. No, we're not declaring, we're declaring a variable of int star. If we have int star here, what should we have as the equal? Should we have like, for example, like a address, or should we have like a number, an int? What do you think? Should we have the address here? Should we have the actual integer of it? Close. So so there are two cases of when we use this star here. The first one is when we're declaring and initializing it. So when we're declaring initialize, we always have int star variable name equal to the actual value. So for example, equals to 5. And the second case we use it is when we dereference the value in like a function here, something like this. So in this case, if we have int star temp equals to a number, what should we do to a? Because a is actually the address right now, so this will return an error if we were trying to run this code. So how do we get the actual value of a, not the address it's pointing to? Ampersand? Close, because a is already the address, right? Yeah. So it should be star, nice, yeah, star a. So now whatever a is, which is 1 here, temp will be that. Okay, so how should we change a equals to b with this dereferencing we did? Okay, so now we have, instead of having just int a equals to int b, we can have star a equals to star b here. And b will equal to temp. Yeah, and then we dereference b equals to temp here. Okay, let's see if this works. Okay, so now we got an error here. Oh, sorry, let me delete the C first. Yep. Okay, so what's happening here is that when we're using temp to swap it, we are, okay, so I think to swap this, we'll just keep temp as an int and swap the actual values of them. Okay, so yeah, we could do this. So this, okay, we can do it like this, where int temp is just an int that's equal to the dereferencing of a. And now the dereferencing of a equals the dereferencing of b. So the int is equals to the int, and the int b equals to temp, which is already an int. So in this case, if we want to print the values again, yeah, so now these values have been swapped here. Does anyone have any questions?
Yeah, so I just wanted to say, to like further clarify why, I don't know if you guys like went through it in your lectures, but when you're swapping something, you always want like a third variable, right? Because it's like the analogy where you have 2 cups full of milk. If you pull like the other one, like that's not swapping it. So you need a third variable to store that before you move it and then swap it. So the reason why like temp is not actually a pointer is just a random variable that's just storing the value of it, which is star 8, right? Temporarily, and then after like, yeah, so it's just helping us swap. So yeah.
I think if you were to do this, wait, yeah, there. Oh, okay, yeah, I see. Okay, yeah. So yeah, this should be so this should be just an int with a dereferencing of a. And this is how you will swap it without returning any values back to main. Because sometimes when you have to return multiple variables like this, it's easier to just pass in the pointer instead of passing multiple ints and finding a way to return it, which could be a lot harder. Okay, so like I said before, in the visualization of this, we have 0x4 and a, that's what it's called, with a value of 1. And after it, we have 0x8 with b, and the value of it is 2. Okay, so now 2 and 1 has been passed into the stack of swap with different addresses than before because they're replicating the variables instead of having the same one. So instead of 0x8, b here is actually 0x40. Yeah, the actual address doesn't matter. So now you're performing a swap, but then after this function finishes, the stack of swap gets destroyed. So now you just have the original declaration here, and nothing actually happens to A and B. Yep. Yep, so this is what I said. You're passing by reference and make the function argument pointers. And instead of passing A and B as ints, you pass in the address, and now creating copies of B, we're passing addresses of the original variables. Okay. Yep. So, okay, now before starting linked list, we're just gonna have a quick break, and the pizza should be coming soon. So just sit around for a bit and chill.
All right. Welcome back, everybody. We will now be talking about linked lists. Okay. So, and just a reminder to stay to the end. We have like a special Q&A about the assignment, so you can ask any questions. So make sure you stay to the end. Okay. Linked lists.
Wait, it's not,
Oh.
it's like frozen.
Oh, yeah.
How do you unfreeze it?
There we go. Okay. There we go.
Yeah.
All right. Linked lists versus arrays. All right. Who can tell me what the difference is? Yep.
And you need the address to connect each
Yeah, exactly. So linked lists, accessing each element, you can only access it through the previous element, whereas an array, you can access it from anywhere. You don't have to be at one single element. And so linked lists, they're dynamically sized. So arrays, they're fixed size, whereas linked lists, they can keep going on to like infinity. Well, not infinity, but like the computer's max memory. And the nodes, they don't have to be stored contiguously in memory. Okay. And linked lists, they can be like deleted or added anywhere without worrying about resizing the structure. So that's kind of like the dynamic thing. And they can be reordered, and they're not random access structures. So that's like, that's kind of annoying, because to get to a certain element, you have to like loop through the whole thing. So that's like of n, which we'll learn later. But we'll get to that. It's very inefficient, basically. All right. So when we want to use linked lists. So when you need to frequently insert or delete elements, and when the number of elements is unknown. So like you could have like, what's an example? Like a shopping list, for instance. Say you don't know how long your shopping list is going to be. It could get very big. You want to use a linked list so that it can go really big. Okay, a node. A node is essentially a piece of data that has, so a node is basically a variable which has a data and a pointer to the next node. So it's kind of like a train. So, all right, do we want to get some volunteers up? Okay, 3 volunteers.
Oh, yeah.
Okay, we want to call it. Okay, yeah, okay. All right, who wants to be the head? Wait, no, okay. Just,
I'll be the head. I'll be the head.
Okay. All right, who are you gonna point to?
Him.
Yeah, okay, like stand in a line.
Yeah.
Okay. So like do this, like, yeah, okay, and then you point to Caillou. Okay, so this is a real life representation of a linked list of strings. Okay, so what is the data you're holding?
Hello.
No, like what's your name?
Oh, Eric.
Okay. And who do you point to?
D.
What's your data?
Dean.
Who do you point to?
Caillou.
Okay, what's your data?
Caillou.
What do you point to?
No.
Okay, good job. All right. So this is, okay, I'm not gonna say it. All right. All right. So how do we make a node? We have to malloc it. So these guys are actually like permanent in memory. The size of a node. Okay. Any questions about that code? Oh, and I'll just quickly point out, like the stab operator, that is specifically for like struct pointers if you want to like edit their data or like any of their fields. Okay, that's what it looks like. Put your hand up if you're the head. Okay. All right. Why do we need a head pointer? Oh. Yeah.
So like it goes through like the whole train.
Alright, so I'm gonna be like a variable and I'm gonna be called head, but I'm actually like a pointer. So I'll point to Eric in this instance. Alright. And yeah, it's basically to keep track of it, so we have a way to access the linked list in the heap. Yeah, that's what it looks like. Alright. Yeah, so they're basically like a snake pretty much. Alright, traversing it. Who wants...
What?
Just say like the current, like who's current in this thing. Alright.
Okay. So to traverse the list, you need to start at the head, which is why we have to keep track of the head. And then, wait, do you guys want to like sit down maybe?
Oh, thanks.
No, like sit on the floor. Yeah, there you go. So, like, we're gonna have to move along the list, right? So if you look at the code, on the screen, who do you think current is gonna be when the while loop ends? The last node? Yeah, pretty much. So it traverses through the list like that, and then it stops at the last node. What if, inside the while loop, what if I had current is not equal to null instead of current next is not equal to null? Where do you think current will be when the while loop ends? At null? Yeah. Alright. So it's really important to be intentional with your stopping condition, because you want to use the two different stopping conditions for like different purposes. So if you use current next equals null, then you're stopping at the tail node. So you want to do that when you want to like add something to the end of the list, for example, or if you want to delete the tail node. But you want to use current next equals null if you want to process every element in the list. So for example, if you want to print the whole list, if you want to free the list, if you want to look for something in the list, or if you want to do something like adding up everything in the list, then you want to use the second stopping condition and stop when current equals null instead of stopping at the last element. All right, so there's a couple of things that we need to be able to do with linked lists, and one of them is we want to be able to insert a node. So the general steps is you traverse to the list to like where you want to insert the node to, and then you stop before the slot in which you want to insert node. Wait, can we get them to sit down? Are we done with them?
Yeah.
Okay, yeah, you guys can like actually sit down. It's chill. And then after you've like found where you want to insert it, you want to create the new node, and then link the new node to the list, and then link the current node to the new node. So I've got a diagram of what that looks like. So we start at the head as always, and then we traverse until we get to the target value, and then we create a new node, and then we initialize its value, and we link the new node to the list, and then we link current to the new node. So what do you guys think will happen if, instead of doing it in that order, if we linked current first before we linked the new node? Like, do you think we can do that? And if not, like, why?
because you set current next into new node, and then new node is current next, which is the new node. So it's like pointing to itself. So like you'll lose like the last two nodes.
Yeah, that's exactly right. So if you do it in the wrong order, then the new node is going to end up pointing to itself, and then you lose access to the rest of the list, and that's like not good. So you want to make sure you like do it in the right order, and you link the new node before you detach the current. All right, just a special case to consider. If you're inserting a node to the head of the list, then make sure you update the head to point to the new node, so that so that we know where the new head is. Yeah. Okay, another thing we want to be able to do with linked lists is deleting nodes. And the general steps to do that is you traverse to the list and find out which node you want to delete. But you want to make sure to keep track of the previous node. So instead of having just a current pointer, you want a previous pointer, and you want to keep track of the node before the one you want to delete. So then after you want to link the previous node to the node after the one being deleted before you actually delete the node itself. So I'll show you a diagram of what that looks like. So we have a current and a previous, and then we're traversing the list until we get to the target value, which is the node that we want to delete. And then we want to link previous to the next node before we delete the current node. And the reason for that is because if we didn't have a previous node and we just like freed current, then the list would get broken and we would lose access to like the second half of the list. And as I said before, like that's pretty problematic. So yeah, it's important to have a previous pointer when you're deleting nodes. Does anyone have any questions so far? Okay, chill. When you're deleting the head, you want to still keep track of the new head because like it's important to have a head pointer, right? But you can't do it like that. So can anyone tell me what's wrong with that code there? Like why can't we delete the head like that?
You lost the address, yeah. Because you free the head first, and then the computer counts out the second where is, so you must to link the second new head first and then the free the head.
Yeah, that's exactly right. So after we freed head, we don't have access to it anymore, so we can't use head in the next line. Yeah, so what you should do instead is use a temporary node. So you assign a temporary node to point to head, and then you change the value of head, and then you free the temporary node so that you don't like cause any errors and you don't lose any data that way. Yeah.
Okay.
Okay, so we're gonna go through some practice problems now. We'll go through the first one and then we'll see if we may or may not go through the second one depending on like time. But yeah. So the first problem is we're asked to write a function which deletes the nth node from the end of the list and then return the head of the updated list. So the general approach to this is we have to first find the length of the list, and then we have to travel the list until we reach the node that we want to delete, and make sure you keep a pointer to previous, because as I said before, like if you don't do that, you can like lose the link to the list. And then you follow the usual steps to deleting the node. So the only like tricky part of this question is the counting, because you're counting from the end instead of the start. So wait, how do I can like live code it to demonstrate. How do we
Yes.
Yeah. Yep.
Should be this one.
Okay. What? Oh, yep. Okay, so wait, does this work? Okay. All right. So the first thing, as we've said, we have to find the length of the list. So we want a variable to keep track of the length. And right now, since we don't have a list yet, we haven't like started counting it, so the length is 0. And then to get the length of the list. Oh, okay. Yeah. To get the length of the list, hold up. I'll make a. What do you guys think our while loop condition should be? Do you think it should be current next is not equal to null, or current is not equal to null if we're finding the length? Current, yep. And then we'll increment length and wait. Yep. We'll increment length, but we should increment current first. So, all right. So we've done that. Okay. Now we need to keep track of, right now current is null, and we can't use current if it's null, because like dereferencing a null pointer leads to issues, right? So we need to make current head again, and we need to keep track of, we need a previous pointer because we're deleting a node, and the reason, right now the previous like doesn't really mean anything because current is at head. So I've just initialized it to null just as like a default value. And this is like one of the most important parts of this question. It's working out how to actually get to the node being deleted. So I'm gonna use a for loop to count the number of nodes that I've traversed. And then since we're deleting it from the end, we need to take length minus position. Yeah, and then make sure you increment the counter. And then we update the previous and current values as we're like traversing it. All right. We've done this part. Oh. And then we need to link, we're gonna free current. So in order to relink the list, we should have, we should set previous next to current next. And then we'll free current. And return the head. Okay, so that's like the basic code for that. But there is an edge case where, can you guys see any like edge cases to this problem that we will need to consider?
This is like the first node.
Yeah, so if we're deleting the head, then like this code, we need to like update this code to account for that case, right? So if we're deleting the head, that means the position is equal to the length of the list. So wait, can you hold it? So I'm going to add a case here. If we're deleting the head, then we follow the usual steps to, deleting the head. So struct node. Yep. And then that should be everything that we need to consider. So I'm going to test the code. CC. All right, so this code already comes with a main function, and basically how it takes in input is you have to input the length of the list, and then input the values in the list, and then you tell it what the position is of the node that you want to delete. So I'm just going to give like a really simple example. So let's do like 1, 2, 3, 4, 5. And then if I want to delete the third node from the end, what number would I be deleting? Just to give you a hint, like 5 is the first node. So you don't start from like 0. When you're counting back, you would start from 1. So can anyone see what the third node would be?
3.
Yeah, it's 3. So the code should return 1, 2, 4, 5 because we deleted 3. And if we want to like be more rigorous with testing our code, we should test the edge case as well. So we'll test. We'll use the same list and we'll test if it works for deleting the head. So we'll go 1, 2, 3, 4, 5. And then, yeah, so that's deleted the head, and that's pretty much all we need to consider for this question. So, yeah. Does anyone have any questions about that problem? No? Okay. That's good. All right. Should we do the next one? Or?
I'll stand with that one.
Okay. There is another problem we could do, or it's about like reversing a linked list, but we could also like just have an open Q&A if you guys have questions about the course or like the assignment, and we can help you with that. So, like, what would you guys rather do? Hands up for the Q&A. All right. Hands up for reversing the linked list. Oh shit, okay. Sorry. All right. So we're given a problem and it says, so we have a linked list and it's sorted in ascending order. And we're given a start node and an end node, which will be inside that list. And the question asks us to reverse the nodes from start to end, including the start and end node. So before we get into coding, I think it'd be helpful for us to go through how we would reverse a list. So let's say we have a really simple list here, and let's say that our start node is 1 and our end node was 3. Then we would need a previous and a current and a next to keep track of the pointers. So the first thing we would do is we need to, the basic approach is we're going to swap 1 and 2, and then we're going to do another swap so that it'll end up being 0, 3, 2, 1, null. So I'm going to quickly show you how to, it's all about rearranging the pointers, right? So the first thing to do is we swap 1 and 2, and then we have to update the next. So the current is always going to be at the starting node, right? And then we have to do another rearranging of pointers like that. So then when we straighten it out again, we've reversed the list. So does that make sense so far? I'll take that as a yes. So let's think about like what we did in those steps to like help us work out. Wait, sorry, yeah?
Wouldn't it be 3210?
Because the start node is 1 and the end node is 3 in this case. Yeah. So we're not like including 0 in the reversal. Does that make sense?
Yeah.
All right. Yeah. So let's have a look at like what steps we took. So the first thing is, as I said, we need a previous and a current and a next, and we need to link current to next, and then we need to set next to current, and then we need to set previous next to next. And now let's look at the second step. So after we update next, we're gonna set current to next. We set next to previous next, and then we set previous next to next, and then we reverse the list. So can you guys see how there's like a pattern? So there's a series of steps which I essentially did twice in order to reverse this list. So can anyone remember what the first step was? So I'll go back to the start.
You point current to next.
Yep, so current is next, and then the second step is you point next to previous next, and then can anyone remember the last step? Yeah, you point previous next to next. And then again, like it's current next equals next, and then next equals previous next, and then that's how you reverse it. So, but there's a few things that we need to do in this problem before we actually reverse the list. So we need to, because we need a previous and a current and a next. So we're gonna first need to traverse the list, and then previous is the node before the starting node. So we're gonna stop one node before the starting node, and then we're going to set current equal to the starting node, and we're going to set next equals to current next. And then when we actually perform the reversal, we're going to need to do the series of steps that we just went through inside a for loop, because the number of times you perform those steps will depend on how many nodes you're reversing, right? So with this example, I reversed 3 nodes, and I did those steps twice. And yeah, so basically the number of times where you need to perform those steps is equal to the number of nodes that you need to reverse minus 1. So we're gonna need to put that in a for loop, and then after we perform the reversal, we just return the head of the list. I haven't set up the starting code for that. So. Oh, are you sure? Yeah, because you need like a main function and stuff.
What's this? Oh, right. This one. We can just talk with it after run.
Okay, sure. Well, alright.
Okay, well, for what is it this?
Yeah, because we need a main function, and I haven't we haven't set it up yet.
How did GPT it?
Sure.
Wait, is this the? Oh, that's.
Yeah.
Wait, what's? Okay. But it might take a while. That's it.
Yeah.
I'll turn it up. Well, let's.
Alright. So we're gonna try and set up the live coding for that, but while we do that, does anyone have any questions about like
C5.
the problem so far?
X for right.
No? Alright, sure.
Okay, that was pretty fast. But yeah, I think it's chill.
Wait, what are you doing right now? Like,
Coding.
Why is it so long?
I don't know.
wait, I have the code for the reversing, but we don't have a main function to like test it and stuff.
Test it.
Yeah,
Oh,
to
just
like show that it works.
oh, we'll just like make a random list then.
Okay.
Yeah, it'll be fine.
Okay.
I think we can use this.
Yeah, yeah.
You want to have a look at it? Append function. So this is just for creating new mode and shit. And then this is like I think
Wait, do you want to make a new like doc for
and
it?
put it over like.
Yeah. Alright.
Copy that over. How?
I'm not gonna copy that over. Wait, freeze it.
How do you fix it?
Wait, is this?
Alright, give us a moment.
Do you have messages?
What?
Do you have
Yeah.
Lucas's?
Oh, I sent it in email.
Oh, so okay. I'll just send him an email with this then. What the fuck is wrong with you? Okay. You know, it's pretty cool. With an email and then.
If this code doesn't work, it's gonna be so embarrassing. Oh?
Well, I didn't change it from like the last time I did it though.
Yeah, can that be? And then
What?
hopefully that is.
Is that the...
Wait, but that's like a complete example. Are we coding it? Or are we just showing the example?
I was gonna... I don't know. What do you think? I was
Just
gonna
code it
code it up, yeah.
Code
Yeah,
it
we
up.
don't need to test it. It's fine.
Okay.
Wait, what? Okay. Wait, do you wanna...
Like, we'll just say it works.
Okay.
Yeah, yeah.
Okay.
Okay. Go back. Yeah.
Yeah.
Okay. Can you all see this? Yeah. All right.
I may as well just show them that then.
No, we want to explain what you're doing.
Yeah.
Okay. So basically, here we're saying if left equals right, then we're going to return head. Oh. Okay.
No one left and right is.
Yeah. Okay, so
Yeah, okay, fine.
left is the start. In this function, we've named left as the starting node and right as the end node. And basically, the first case he's doing is if the starting node is equal to the ending node, then there's nothing to reverse. So you just return the head of the original list. And right now, what he's doing is we're creating a dummy variable, which is a variable that comes before the head, and we're just initializing the previous prev to the dummy variable. And the dummy variable doesn't really mean anything. It just makes things a bit easier for I guess handling, yeah. Okay, and then with the first for loop, what he's done is he's traversing the list, and then we've stopped before the left node. So we've stopped before the starting node because that's where previous needs to be in order to anchor the reverse part of the list. And then he's initialized current, and now he's starting the actual reversal process. So inside the for loop, he's keeping a counter, and the reason the for loop is going to run, so wait, first of all, how many times is the for loop going to run? Does that make sense? Did that question make sense? Yeah, how many iterations is the for loop going to run in terms of right and left? that's okay. With the stopping condition in the for loop, we're stopping the for loop when I is equal to right minus left. So basically, it's the end node minus the start node minus 1 because we're starting from 0 and like we're doing like a less than and not less than equal to. And the reason for that is because remember how I said when you're reversing a list, the amount of times you need to perform those steps is equal to the number of nodes that you need to reverse minus 1. So when you take the end node minus the start node, you're essentially finding that's equal to the number of nodes that are being reversed, and then like minus 1. And so inside the for loop is the steps that we talked about. So we have a next that we update each iteration, and then we have current next equals next next, and then next next equals previous next, and then previous next equals next. So that's the actual like reversal part. And then since we've set dummy as like a new node that comes before the head, we're returning the head of the updated list, so we return dummy next. Does that make sense to everyone? All right, chill. Is that it?
Yeah.
Yeah.
Okay, that pretty much wraps it up. Yeah, that's what the code looks like. So thank you guys. That pretty much sums up our COMP1511 lecture. Do we have any questions about any of the content? It can be about like the final exam. It can be about the assignment as well. We're happy to answer anything. No? Okay, thank you.
Thank you
Thank you for
guys.
coming.
Good luck.